What if I told you that one of the most influential engines in automotive history made less horsepower than a modern Honda Civic? That the engine that would go on to power everything from British sports cars to Formula One racers, from Range Rovers to experimental aircraft, started life being mocked for its modest output? 155 horsepower, that's it. In an era when Detroit was cramming 400-plus cubic inches under every hood and chasing horsepower numbers like they were going out of style, General Motors built an engine that made about as much power as a base-model family sedan today. Critics laughed. The press yawned. Muscle car enthusiasts dismissed it as a joke. When they were all wrong. Monron, picture this. It's 1960, and you're an engineer at General Motors. The company brass has just handed you an impossible assignment. Create a V8 engine for the new compact car lines. Make it smooth, refined, and economical. Oh, and one more thing. It needs to weigh less than 320 pounds, complete, with all accessories. For context, the small block Chevy V8, considered lightweight for its time, tipped the scales at over 500 pounds. You're being asked to cut 40% of the weight from an already efficient design. The typical response would be to shrink displacement, reduce cylinder count, or compromise on durability. But what if there was another way? This is the story of the Buick 215 V8, an engine that proved power-to-weight ratio could trump raw horsepower, that handling could beat straight-line speed, and that sometimes the biggest innovation comes from subtracting, not adding. It's the story of how aluminum changed everything, how British engineers rescued American innovation, and how an engine designed for grocery-getting compact cars became a legend in motorsport. To understand why the 215 was revolutionary, we need to travel back to the late 1950s. Detroit was in the middle of a horsepower war that would make today's performance battles look civilized. Chrysler had just introduced the 392 Hemi. Ford was preparing the 427. Chevrolet was developing the 409. Pontiac had cracked the 400 cubic inch barrier. Every year brought bigger engines, more power, more weight. A typical American V8 of the era weighed between 600 and 750 pounds. Some of the big blocks pushed past 800. But cracks were starting to show in this bigger is better philosophy. Insurance companies were raising rates on high-performance cars. Gas prices were creeping up. Foreign imports like the Volkswagen Beetle were starting to gain traction with their efficiency and practicality. Most importantly, a new generation of buyers was entering the market, people who wanted something different from their parents' land yachts. And when General Motors saw this shift coming. In 1959, they launched a massive development program for a new line of compact cars. Chevrolet would get the Corvair with its air-cooled rear engine. Pontiac would develop the Tempest with its radical flexible driveshaft. Oldsmobile would create the F-85, and Buick would introduce the Special. But there was a problem. While Chevrolet had their unique flat six for the Corvair, the other divisions needed a conventional engine that would fit these smaller platforms. The existing V8s were too heavy, too thirsty, too expensive. Enter Joseph D. Turley, a brilliant engineer working for Buick. Turley had been experimenting with aluminum engine components since the early 1950s. He understood something that most of his contemporaries dismissed, that reducing weight could provide benefits that went far beyond fuel economy. Less weight meant less stress on suspension components, better weight distribution, improved handling, faster stopping, less inertia to overcome during acceleration. While everyone else was chasing horsepower, Turley was chasing efficiency in its purest form. The development program began in earnest in 1958. The target specifications seemed impossible. The engine needed to weigh under 320 pounds, produce at least 150 horsepower, run on regular gasoline, be reliable enough for mass production, cost no more than 20% above a conventional iron engine, and be ready for production by fall 1960. That gave the team less than 2 years to revolutionize engine design. Second sense in the first challenge was metallurgy. Aluminum had been used in racing engines before, but those were hand-built, cost-no-object designs. The 215 needed to survive mass production, dealership mechanics, and owner neglect. General Motors partnered with Reynolds Metals Company, who had been developing new aluminum alloys specifically for automotive use. The alloy they selected, Reynolds 355, contained silicon for fluidity during casting, copper for strength, and magnesium for hardness. It could withstand temperatures up to 400 degrees Fahrenheit without significant loss of strength. But aluminum brought its own problems. It expands and contracts at nearly twice the rate of iron when heated. This meant conventional head gasket designs would fail within thousands of miles. The solution? A special composition gasket with a steel core, surrounded by soft copper facings, with a special coating that would maintain seal integrity through repeated heat cycles. Each gasket cost 3 times what a conventional one did, but it worked. The cylinder walls presented another challenge. Aluminum is too soft to handle piston rings directly. The team developed a process where iron cylinder liners were cast in place during the block molding process. The aluminum would shrink around the iron as it cooled, creating a mechanical bond stronger than any adhesive. But the tolerances were insane. If the aluminum cooled too quickly, it would crack, too slowly, and the bond wouldn't hold. The foundry workers had to maintain casting temperatures within a 5-degree window. Then came the valve train. In a conventional engine, you could machine the lifter bores directly into the iron block. With aluminum, the lifters would quickly wear through the soft metal. The solution was pressed-in iron bushings for each lifter bore. 16 additional parts, 16 additional assembly operations, 16 more chances for something to go wrong. The cylinder heads were equally complex. The valve seats and guides needed to be made from special austenitic iron that wouldn't work loose as the aluminum expanded and contracted. They had to be installed with an interference fit precise to 3/10,000ths of an inch, too tight, and the aluminum would crack. Too loose, and they'd fall out after a few heat cycles. Here's where it gets interesting. The basic architecture was pure traditional American V8, 90-degree bank angle, overhead valves, single camshaft in the block, hydraulic lifters, push rod actuation, nothing radical there. The bore was 3.5 inches, the stroke was 2.8 inches. Total displacement came to 215.5 cubic inches, or 3.5 liters in metric terms. The compression ratio was set at 8.8.1, allowing it to run on regular gasoline. But look closer at the specifications, and the innovation becomes clear. The complete engine assembly, including flywheel, water pump, and exhaust manifolds, weighed just 318 pounds. A comparable iron V8 of the same displacement would weigh nearly 500 pounds. That's a 180-pound weight saving, equivalent to leaving a full-grown passenger behind. The block alone weighed just 35 pounds. You could literally pick it up with one hand. The initial output was rated at 155 horsepower at 4,600 RPM and 220 pound-feet of torque at 2,400 RPM. By today's standards, those numbers are laughable. A modern 4-cylinder Camry makes more power. But remember, this was 1960. The average American car made about 1 horsepower per cubic inch. The 215 was making 0.72 horsepower per cubic inch on regular gas with a 2-barrel carburetor. Not spectacular, but respectable. And General Motors hedged their bets with multiple versions. Buick's variant used a 2-barrel Rochester carburetor and produced those baseline 155 horses. Oldsmobile's version got a 4-barrel carb and made 185 horsepower. Pontiac's edition, with higher compression and a 4-barrel, pushed out 190. Later, Buick would offer a 4-barrel version making 185, and a rare turbocharged variant producing 215 horsepower, 1 per cubic inch, the holy grail of naturally aspirated performance at the time. End production began in summer 1960 at GM's Flint, Michigan facility. The manufacturing process was unlike anything the auto industry had seen. The aluminum blocks required special handling equipment. They were too light for the existing conveyors designed for iron blocks. The machining tools needed different speeds and feeds. The assembly line workers had to be retrained to handle the lower torque specifications. Over-tightening a bolt would strip the threads right out of the aluminum. Once. The first cars equipped with the 215 hit dealerships in October 1960. The Buick Special, Oldsmobile F85, and Pontiac Tempest became America's first mass-produced cars with aluminum V8 engines. The automotive press was intrigued but skeptical. Motor Trend tested a Buick Special with a 155 horsepower engine. 0 to 60 took 13.2 seconds. The quarter mile required 19.1 seconds at 69 miles per hour. Adequate for the era, but hardly exciting. But then, something unexpected happened. Racers started buying these engines, not for their power, but for their weight. Mickey Thompson, the legendary speed record setter, immediately recognized the potential. He bought a 215 and started experimenting. With just basic hot rodding tricks, porting, polishing, headers, and carburation, he was seeing 250 horsepower. That's 0.78 horsepower per pound of engine weight. A 327 Chevy, making the same power, had a ratio of 0.5 horsepower per pound. The implications were staggering. In a 2,500-pound race car, switching from an iron V8 to an aluminum 215, making the same power, was like adding 30 horsepower just from weight reduction. But it went deeper than that. The lighter engine meant less weight on the front wheels, better turn-in, less understeer, reduced tire wear, lower unsprung weight if used in a front-engine car. The suspension could be softer while maintaining the same handling characteristics, improving grip, and Dan Gurney, the Formula One and Can-Am racing legend, put it perfectly. Everyone was obsessed with making more power, but power you have to accelerate. Weight is always there, slowing you in the corners, fighting you under braking, wearing out components. The 215 understood this. And soon, the 215 was showing up in places GM never imagined. Harvey Aluminum Special Indy cars, Brabham Formula One cars, where Jack Brabham himself used a variant of the 215 to win races. Sports racers, drag cars, even experimental aircraft, where the power-to-weight ratio made it ideal for small planes. But here's the kicker. While racers were falling in love with the 215, General Motors was falling out of love with it. The aluminum engine cost approximately 35% more to manufacture than an equivalent iron engine. The dealers were struggling with repairs. Many mechanics didn't understand the different maintenance requirements. You couldn't just swap in standard parts. The special gaskets, the iron inserts, the precise tolerances, everything cost more and required special ordering. Engine warranty claims started piling up. Owners who ignored cooling system maintenance would overheat the engines, causing the aluminum heads to warp. Mechanics unfamiliar with the design would over-torque bolts, stripping threads. Some dealers refused to work on them altogether. The most common failure? Antifreeze neglect, leading to electrolytic corrosion between the dissimilar metals. The aluminum would literally dissolve from the inside out, and the production numbers tell the story. In 1961, the first full year of production, GM built 326,156 engines. In 1962, that dropped to 301,244. By 1963, the final year, just 148,362 rolled off the line. In March 1963, General Motors made a shocking announcement. They were discontinuing the 215. The official reason was cost and complexity. The real reason was that GM had developed a cheaper solution. The Chevy 2's new inline-six and small V8 could be shared across divisions at lower cost. But the story doesn't end there. Not even close. Enter Rover, the British car manufacturer. In 1964, Rover's managing director, William Martin Hurst, was visiting the United States. He noticed a Buick Special in a rental car lot and was intrigued by its smooth, lightweight engine. Rover had been searching for a modern power plant for their luxury sedans and the upcoming Range Rover project. Their existing engines were heavy, agricultural units dating back to World War II. Martin Hurst approached General Motors about licensing the design. GM, happy to recoup some development costs from what they considered a failed experiment, sold the complete rights, tooling, and production equipment to Rover for a reported $750,000. Adjusted for inflation, that's about $7 million today. For an engine that had cost GM an estimated $40 million to develop, when Rover's engineers, led by Spen King, immediately set about improving the design. They increased the bore to 3.56 inches, raising displacement to 3.5 liters. They redesigned the cylinder heads for better breathing. They developed new camshaft profiles for more torque. They fixed the corrosion issues with better coolant specifications and improved gasket designs. Most importantly, they understood what GM had missed. This wasn't an economy engine. It was a premium lightweight performance unit. And that's the Rover V8, as it became known, transformed British motoring. In the Rover P5B luxury sedan, it provided smooth, effortless power with none of the weight penalty of traditional British engines. In the Range Rover, introduced in 1970, it enabled a combination of on-road performance and off-road capability that had never been seen before. The lightweight engine meant less stress on axles, transfer cases, and drive lines when bouncing over rough terrain. But it was in sports cars where the Rover V8 truly shined. Morgan used it in their Plus 8, creating one of the fastest accelerating cars of the 1960s. TVR installed it in everything from the Griffith to the Chimera. Marcos, Ginetta, and dozens of other small manufacturers adopted it. The engine became the default choice for British performance cars, and the specifications evolved continuously. By the 1990s, Rover had pushed displacement to 4.6 liters through increased bore and stroke. Power outputs reached 280 horsepower in factory trim. Aftermarket specialists like JE Engineering and Overfinch were extracting over 400 horsepower. The same basic design that had been mocked for making 155 horsepower was now producing nearly triple that figure. Let's talk about what made this engine so special from an engineering perspective. The combustion chamber design was remarkably efficient. Despite being designed in the late 1950s with slide rules and drafting tables, the chamber shape promoted excellent flame propagation. The wedge design with canted valves provided good breathing without the complexity of hemispherical heads. The short stroke meant low piston speeds even at high RPM, reducing stress and friction. And the aluminum construction provided benefits beyond weight. Aluminum conducts heat 3 times better than iron. This meant more consistent cylinder temperatures, reducing hot spots and detonation. The engine warmed up faster, reducing cold start wear. The improved heat rejection meant smaller radiators and less cooling system complexity. In racing applications, the rapid heat dissipation allowed tighter tolerances and more aggressive tuning. The compact external dimensions were another advantage. At just 26 inches wide, 28 inches long, and 27 inches tall, it would fit in spaces where other V8s couldn't. This opened up installation possibilities in everything from kit cars to aircraft. The low deck height meant a lower center of gravity. The narrow width allowed for better packaging of exhaust and accessories. And manufacturing techniques pioneered for the 215 influenced the entire industry. The cast-in-place cylinder liners became standard practice for aluminum engines. The special gasket designs evolved into modern multi-layer steel gaskets. The precision casting techniques developed for the 215 enabled the thin wall casting used in modern engines. Even the failure modes taught valuable lessons. Modern aluminum engines use iron-based coating processes pioneered to solve the 215's wear issues. Consider the racing success. In SCCA competition, 215-powered cars dominated the under 3.5-liter classes through the 1960s. The Repco Brabham Formula One engine that powered Jack Brabham to the 1966 World Championship was based on the 215 architecture. That's right. A motor designed for American compact cars won the pinnacle of motorsport. The Repco variant used the Oldsmobile block design, bored and stroked to 3 liters, with custom cylinder heads and fuel injection. It produced 300 horsepower at 8,000 RPM, nearly double the specific output of the street version. When in drag racing, the 215's lightweight made it perfect for altered wheelbase cars where front end weight was critical. In road racing, the superior weight distribution transformed handling. In rallying, the combination of lightweight and reliability made it a favorite. Even in powerboat racing, where weight affects planning and handling, the 215 found success. But perhaps the most impressive achievement was longevity. Rover continued production until 2004. That's 44 years of continuous manufacturing, making it one of the longest produced engine designs in history. Land Rover used variants until 2006. The last application was in the Discovery 3, where a 4.4-liter version produced 295 horsepower. From 1960 to 2006, 46 years of evolution from the same basic architecture. And in chunks, the aftermarket support remains strong even today. Companies like D&D Fabrications, Real Street Performance, and British V8 specialist firms offer everything from complete rebuilt engines to 5-liter stroker kits, producing over 400 naturally aspirated horsepower. Forced induction setups push beyond 600. Modern engine management and fuel injection have solved the carburation issues that plagued early versions. Improved materials have eliminated the corrosion problems. Let's put this in modern context. Today, aluminum engine construction is standard. Every manufacturer uses it. But in 1960, it was considered impossible for mass production. The 215 proved it could be done. The weight savings that seemed insignificant then are now considered crucial. Modern engineers obsess over every pound, understanding what the 215 demonstrated, that weight reduction multiplies every other performance parameter. The influence extends beyond just materials. The 215 proved that smaller displacement with advanced materials could match larger conventional engines. This philosophy drives modern turbo 4-cylinders that outperform V8s from just a decade ago. The focus on power to weight over absolute power is now standard design practice. Every Formula One engine, every supercar motor, every high-performance motorcycle engine follows principles the 215 pioneered. And consider modern examples. The Ford EcoBoost 3.5-liter V6 makes 450 horsepower and weighs about 450 pounds, 1 horsepower per pound. Impressive until you realize hot-rodded 215s were achieving similar ratios in the 1970s. The latest Corvette LT2 V8 makes 495 horsepower and weighs 465 pounds. Again, about 1 horsepower per pound. The 215 architecture, fully developed, could match these power-to-weight ratios decades earlier. The lesson is profound. Innovation isn't always about adding complexity. Sometimes it's about finding elegance in simplicity. The 215 didn't have variable valve timing, direct injection, or forced induction in its original form. It succeeded through fundamental engineering, right materials, right size, right weight. It proved that questioning basic assumptions could yield revolutionary results. The financial impact was equally significant. While GM considered the 215 a failure, selling the rights for less than $1 million, Rover built millions of engines over 4 decades. The Range Rover alone, powered exclusively by variants of the 215 for its first 24 years, generated billions in revenue. Morgan, TVR, and other sports car manufacturers built their entire business models around this engine. The aftermarket industry supporting these engines continues to generate millions annually, and in end-to-end racing success translated to showroom sales. Every victory by a 215-powered car validated the lightweight philosophy. Customers began understanding that a lighter car with less power could outperform a heavier car with more. This shifted market demands, forcing manufacturers to consider weight in their designs. The modern obsession with carbon fiber, aluminum space frames, and weight reduction can trace its roots back to lessons learned from the 215 Nenyen. The human story is equally compelling. Engineers like Joe Turley, who championed aluminum construction against significant internal skepticism, proved that innovation requires not just technical skill, but courage to challenge convention. Spen King at Rover, who recognized the engine's potential when its own creators had given up, demonstrated that sometimes innovation means seeing value where others see failure. Racers like Mickey Thompson and Jack Brabham, who immediately grasped the weight advantage, showed that true performance understanding goes beyond headline numbers, and that the technical challenges overcome during development advance manufacturing science. The precision required for aluminum casting pushed foundry technology forward by decades. The metallurgy research conducted for the 215 contributed to aerospace developments. The joining techniques for dissimilar metals found applications in everything from aviation to architecture. Even the failures contributed knowledge, understanding of galvanic corrosion, thermal expansion mismatches, and fatigue characteristics that informed future designs. Modern engineers studying the 215 marvel at what was achieved with 1950s technology. No computer modeling, no finite element analysis, no CAD systems, just slide rules, experience, and methodical testing. The fact that the basic design remained viable for nearly half a century testifies to the fundamental soundness of the engineering. Modern additions like fuel injection and engine management enhanced the design but didn't replace it. The cultural impact extended beyond automotive circles. The 215 became a symbol of American innovation, adopted and perfected by British engineering. It represented globalization before that became a buzzword. It showed that good ideas transcend corporate and national boundaries. The engine became a bridge between American and British automotive cultures, respected equally on both sides of the Atlantic. Net collectors today prize 215 equipped vehicles, original Buick Specials, with the aluminum V8 command premium prices. Early Rover P5Bs are considered classics. Range Rovers with the original 3.5-liter fetch surprising amounts. Even projects cars with salvageable 215s attract attention. The engine has achieved iconic status, recognized as a pivotal moment in automotive development. The specification sheet tells only part of the story. Yes, it made 155 horsepower initially. Yes, it weighed 318 pounds. Yes, it displaced 215 cubic inches. But those numbers don't capture the revolution it represented. This was the engine that proved aluminum could work in mass production. That demonstrated weight mattered as much as power. That showed innovation could come from subtraction rather than addition. That validated thinking differently about fundamental assumptions. And so what's the real legacy of the Buick 215 V8? It's not just about aluminum construction, though it pioneered that for mass production. It's not just about weight reduction, though it proved that crucial. It's not just about longevity, though lasting 46 years is remarkable. The real legacy is proof that revolutionary thinking doesn't always mean complexity. Sometimes the biggest leap forward comes from questioning the most basic assumptions. Reengineering the 215 asked a simple question. What if we made it lighter instead of more powerful? That question changed everything. It influenced engine design for decades. It enabled vehicles that couldn't have existed otherwise. It proved that efficiency could be exciting. It demonstrated that innovation could come from any source, be rescued from failure, and find success in unexpected places. Every modern aluminum engine owes something to the 215. Every engineer who prioritizes weight reduction learned from its example. Every racer who understands that power-to-weight beats pure power follows principles it established. Every manufacturer using mixed metal construction builds on problems it solved. The little engine that made just 155 horsepower changed the automotive world more than motors making 3 times that power. And then today, as manufacturers chase efficiency through complexity, 48-volt mild hybrids, cylinder deactivation, infinite variable transmissions, the 215 stands as a reminder that sometimes the best solution is the simplest. Make it lighter, make it reliable, make it adaptable. The fundamentals that made the 215 successful remain relevant. Physics hasn't changed. Weight still matters. Efficiency still counts. Innovation still rewards those who question assumptions. And the Buick 215 V8 proved that you don't need the most power to win. You need the right power in the right package. It showed that 155 horsepower in 318 pounds could beat 300 horsepower in 600 pounds. It demonstrated that engineering excellence isn't always about maximum specifications, but optimal solutions. It validated thinking differently when everyone else was thinking bigger. That little aluminum engine that everyone dismissed, it outlasted its critics, outsold its competitors, and outlived its creators' expectations. It powered everything from luxury sedans to Formula One champions. It proved that sometimes the best ideas are the ones that seem too simple to work. It showed that revolution can come in small, lightweight packages. What's your take on engines that prioritize efficiency over pure power? Have you experienced the difference weight reduction makes in vehicle dynamics? Drop your thoughts in the comments below. If you enjoyed this deep dive into one of the most underappreciated engines in automotive history, make sure to subscribe for more stories of engineering innovation that changed the game. Until next time, remember, sometimes less really is more, especially when that less weighs 180 pounds less than the competition.